just they couldn't run any sims?
No, like there's a way like went up.
Oh. But I thought it only went up because they did some they upped the power. And it
Seems like everybody's still working hard. All right. Good morning or whatever it is, afternoon, evening. I don't really know. I just got off the plane from Seoul about an hour and a half ago. So it's been a long day. Actually, I taught this is the first time I'm teaching a lectures at 2 times of the ocean in the same day. So I already did 2.5 seminar this morning at Samsung in Seoul. So got on the plane just in time back for here. Good. World is small. Anyhow, this is. So this is why the lecture notes were not posted really on time. So, but they're on the computer now, so you should be fine. And they will be available, I think, in the next hour or so. Anyhow, good. So, any questions on the project? I know you have about a couple of hours left, but those of you who are here must probably be finished. That's my assumption, but at least with this phase. So, after this phase, what we're really going to do now is execution, and I'm going to post this probably tomorrow. Yeah, you will see tomorrow what the next expectations are. But it's really as execution of what you have now proposed. It's really turning into the real design, getting some layout done, do some analysis on it, and figure out how close what you end up with after simulation, things like that, is close to what you expected to happen after this first sort of preliminary analysis. Okay? So we will try to get you really quick feedback hopefully by the end of the week about if there's particular challenges you see with the proposal you have right now. So we are now Wednesday, week 13. The poster session is going to be exactly 2 weeks from now. Okay, so it's going to be on Wednesday of the last week of lectures. We're going to basically take a whole afternoon and have posters. This is going to be at the Wireless Center. I'll give you a lot more information about how the posters have to be structured. But this is going to be your opportunity to, rather than writing it down, give you the opportunity to explain verbally what you were thinking, how it went, what didn't go pan out, and things like that. It's a lot more effective than kind of trying to write it down. So that will be exactly 2 weeks from now. Okay, good. So any questions? Things are going well? You got basically things zippingly fast or zippingly low power or whatever it is? So we'll see. I'll let you know. I'll give you some feedback later on. Anyhow, good. So We have homework 8 posted. As I mentioned, this is the last graded homework of the semester. We're going to give you one more, but that's basically just for yourself to have the capability to make some exercise before the final. The project phase 2 is due today. Don't forget the hardware lab. And also, if you want to get any regrades on midterm 2, that's today. So I'm going to be in my office after lecture. So if you have any questions, issues, let me know. Okay. That's that. So what we're going to do today is continue on timing. We just kind of started scratching a little bit on the surface, give you the basic idea of what timing constraints are. We're going to continue that, and then we're going to, at the end of this, we're going to start rolling into wires. We haven't talked too much about wires yet. I kind of pushed it back because of the project. Typically, I like to do it a little bit earlier, but I pushed it a little bit back in time because of the fact that we wanted to do arithmetic first and all this kind of things, which are necessary for the project. But do not ignore wires. As I said, I was over in Seoul, heard a bunch of presentations from companies like Samsung and a bunch of faculty or people working in the extreme scale. It turns out that if you look at the 32 nanometer node, most of the performance of, let's say, the latest microprocessors are going 45 nanometers, 32 nanometers. Actually, the performance of the circuit is now really determined by a transistor driving metal wires. So it's not anymore by the intrinsic capacitance or the fan-out capacitance of the gates. It's really the metal wires that connect them is the dominant factor of the performance of those devices. So another interesting thing I learned is that most people now start to believe that scaling will continue. 45 is definitely happening. Intel is shipping 45 nanometers. 32 nanometer node, people are doing prototyping stuff. 22 will definitely happen. Nobody's clear if you're going to do scaling after 22 nanometers. That's a very big unknown. And there's a number of arguments that say actually scaling below 22 nanometers are going to make the circuits actually go slower again. So there's some interesting trends going on there. But it's interesting to observe that these things are, that a lot of people are thinking about how we're going to keep on scaling devices and what the benefits are going to be and so on and so forth. Anyhow, brings us to timing. So I showed you last time, you basically, timing constraint is you also have to look at it the following way. The timing or the clock speed of a circuit is determined by the time I create, let's say if I have edge-triggered flip-flops, I have a rising edge on the clock on a register, and what we want to make sure is that at the rising edge, the next rising edge at the following register, that all the data is stable. Right? That's really what you want to have. Get a clock edge, data starts propagating through the network, and it has to be totally ready before the next clock edge comes in. Okay? And that's going to determine your clock period. Now, we can write down the equations for that. And that's where we ended last lecture. So you have your combinational logic. Clock edge comes in. It takes a certain clock to Q delay before the output of the register starts changing. Then data is going to propagate to the combinational logic. And we have to look at the worst case delay. We look at all the critical paths, and we say, or the paths, and we say the critical path is the one with the longest delay. So after that, data is going to be stable here. And we also know that before we basically can apply the next clock edge, we have to make sure that we basically, or that we maintain or are supporting the certain setup time. We have to make sure that the setup time requirement is not violated. The data has to be stable for a certain amount of time before I can apply the next clock edge. And that's what the setup time does. So that's really determined the clock period. It's that sum of those three elements. Okay? So that's the one very important constraint on when you do, let's say, a big microprocessor design. You have to make sure that this constraint is met everywhere. Okay? But there's another one. And the other one is this is on the slow side. There's one which goes on the fast side. And we call that the raise margin constraint. Raise margin constraint says, if I apply a clock edge, bingo, data starts going, it might be that your data goes really, some paths are really short. So the data starts zooming through the logic and appears at the output of the block quite rapidly. And we know that this register here has a hold time constraint. The hold time constraint says the data has to be stable a certain time after the clock edge is basically removed, or after the clock edge basically is applied. So we want to make sure that this very short path, which consists of the CTQ, the minimum CTQ delay, plus the minimum delay to the logic, is going to be larger than the hold time. Okay? Now you can imagine, suppose for instance I would have two registers just next to each other. You can see that in that case you might have some problems, because the minimum delay of the logic in between here is 0. So if you kind of start stacking registers very close to each other, checking the hold time constraints is going to be very important. Okay? So that's the basic equation. However, this assumes that our clocks are ideal. Right? It assumes that this clock here, TCLK1 and TCLK2, are exactly the same. Which means that everywhere on our chip we have a uniform definition of time. Okay? Exactly the same time. It looks like you have a global clock there that basically says, a universal clock that says, hey, this is this time with absolute precision. In reality, that's not happening, because the way we do a chip, let's say a microprocessor, what you're going to have is somewhere an external crystal running at a certain clock frequency. That's your clock reference. You bring another chip, and the first thing we're going to do is multiply it upwards. We multiply the clock, because if you say I have a 2 gigahertz or 3 gigahertz type of clock frequency on my chip, bringing a 3 gigahertz clock signal from the board onto the chip is very impractical. So we really would like to have something which is 100 megahertz, something like that. We bring another chip, and then we have a clock multiplier, something that multiplies the clock frequency. You buffer it off, and then you distribute it to the chip. Distributing to the chip means you're going to have a delay to the wires, delay to the buffers, drivers, and so on and so forth. The lecture notes are not ready yet, unfortunately, so don't search for them. You won't find them. Maybe this part is actually part of the previous lecture, so you could find them in there. So there's a set of clock non-idealities that are there. Very important one is what we call clock skew. Clock skew can be seen as follows. So I have my clock coming in here, and I have, say, a register here, register here, register here, okay, or a register there. So now what I'm going to do is, from the central clock source, I'm going to use wiring to distribute my clock to those different registers. Okay? As you see right away, the length of the wires that goes to those different clock registers is going to be different. There might be also different load factors on there. There might be more registers connected on one side than on the other side. Bottom line is the clock won't arrive exactly at the same time at those different registers because of the different delay factors. That is what we call skew. It is a spatial variation in a temporally equivalent clock edges. So you have another clock edge that's supposed to be temporally equivalent. They have to be on the same edge, but because of the fact that our registers are different placed on a chip, we're going to have spatial variations. Now, some of that is going to be deterministic. You can do layout and do the analysis of the wires and say, okay, this wire is longer than that one, here's my delay. This is going to have so much skew. But it's also going to be a random component. And random component because of the fact, for instance, that I might have buffers on my clock wires. And my buffers on my clock wires might have, let's say, different ground bounds or noise coming in from the supplies. The delay of those buffers might vary. So you can imagine that one buffer here and buffer there might experience different type of random effects. So your clock skew will be a mean value, and there will be some variation around it because of some random effects that are happening. Okay? So that's number one, clock skew. Very important. And we'll come back in a minute. Second one is clock jitter. You will have heard, some of you have taken analog classes or RF classes for sure, if you maybe 142, they might have talked about clock jitter or jitter. Jitter is that, suppose I have a register here, single register on the chip, and I have a clock edge. You would assume that the signal that will come in here will be a perfectly periodic signal, right? Perfect period. The period is always going to be exactly the same, clock cycle after clock cycle after clock cycle. Again, that's not going to be true, because what you can see is from period to period, you might see some change on that clock edge. Again, there's some effects that might be due, for instance, to ground bounds. In my supply, I have a clock driver. If my clock varies a bit, the delay of my buffer is going to vary a little bit. So we'll see that this edge is going to go back and forth a little bit. This has a random component to it. Okay? That's what we call jitter. And obviously, I would like to make jitter as small as possible. If I can make it perfectly fine, as we'll show you in a second, jitter basically is overhead. It's time lost. So we want to make jitter and skew as small as possible. There's also variation of the pulse width. Right? If I have a certain pulse that's 50% duty cycle, let's say, on my clock, that might vary. Now you might imagine that in edge-triggered flip-flop designs, that doesn't matter at all. Like in edge-triggered designs, I only care about when the edge arrives. But if I have latch-based design, the length of the duty cycle is important because you determine how long the thing is going to be transparent or not. So in edge-triggered designs, don't worry too much about pulse width. In level-sensitive, latch-based design, you have to. Okay? So these are those non-idealities in the clock. And this is where design for clock of timing networks is really going to be crucial, making sure that these things are small. Just to show you again where they might pop up, where those non-idealities might pop up. So as I mentioned, first thing is that we have clock generation. And clock generation is we go crystal of the chip, we come on the chip. First thing you will see is probably a phase lock loop. Now, most of you have never heard in your life about a phase lock loop, and that's okay. We're not going to talk about it in this class anyhow, but if you are ever going to graduate school or something like that, or you work in any company doing microprocessor design, you will hear more about phase lock loops than you ever want to know. It's a very important part that basically helps you to calculate, but it's also clock multiplication. Okay, that's the first element. Out of this comes your 3 gigahertz clock, let's say. And then I'm going to start distributing that clock over the chip. And there's going to be device variations. Now the way we're going to distribute this over the chip is by using, first of all, this is going to be a long wire. Huge capacitance. Now remember, in order to drive huge capacitance, what do? We provide buffers. And remember the buffers, these are these cascaded chains of inverters. Small inverter, bigger inverter, bigger inverter, bigger inverter, bigger inverter. So there's going to be a bunch of those. And now suppose I have 2 of those, like one goes to the left side of the chip, the other one to the right side of the chip. You might imagine that because of variations in device thresholds or channel lengths of the transistors, those buffers are not going to be identical. Even though you design them identically, variations will make sure that the delay is going to be somewhat different. So I already get some skew out of that. The power supply. As we mentioned before, the power supply, you will always think that's an ideal line, but the power supply typically looks like this. The clock edge comes in, clock edge comes in, and then you have some ripple on it. Every time I draw current out of that clock supply network, I'm going to have a little bit of a voltage drop. And I'll show you later, there's also some inductive stuff in there. So that's why you get these ripple things. So you can imagine that if I have this thing happen on the supply rail of a buffer, that my delay is going to vary. So this causes jitter, for example. Then you have your interconnect, which is an RC wire. We're going to talk more about RC wires soon. It has delay. But now you can again imagine that if I have long wires on a chip on metal, that even though you design them very carefully to be the same delay, there's going to be some variation in the thickness of the wires, and so on and so forth, neighboring effects, all those kind of things. Thickness of the wires is going to change the delay. Height of the wires is going to change the delay. Typically, the height of the wire is determined by this process which is called CMP, chemical mechanical polishing. It's like grinding with sandpaper, kind of. Now, you can imagine that's not going to be exactly the same over the whole wafer. The wafer thickness might change. Actually, I'm going to try to show you pretty soon a 12-inch wafer. I'm trying to get a hold of one. You can see how big those things are. Trying to make this thing totally flat over a wafer like that is going to be very tough. Okay? So variations in that. Again, you will see difference. It's going to cause skew. The capacitive load at the end of the wire might be different. Right? Depends how many flip-flops I connect to that, Also, there's variations in the different flip-flops and so on and so forth. Again, a differentiation. Coupling to adjacent wires. So clock wires go all over the map. So if I now have a neighboring signaling wire that flips back and forth, has capacitive coupling to it, might actually change a little bit my clock signal. So that's another reason. And temperature. Temperature might change the delays of the buffers, and some parts of the chip might be hot, some parts of the chip might be cold. You can see that's going to have an impact on delay. So many reasons why we're going to have jitter and clock skew occurring. And what I'm going to show you now is how those two things are going to impact basically my delay or my clock frequency and my constraints on design. So clock skew, let's come back to the definition. So you have registers, and we look at a clock delay. So typically what I'm going to do as a designer, I'm going to design my clock network in such a way that most of the, presumably, most of my blocks are going to have the same delay. Right? You see the same delay from clock driver to the register. But due to all the effects I just showed you, that's not going to happen. We're going to get a distribution. Some registers will see the clock arriving early. Some registers are going to see the clock arriving late. Okay? So we know that this has a distribution, and we have to know what the extremes of those are, because that's going to help us to determine how fast we can clock it, and also what the minimum, how we basically have to deal with this hold time violation constraints. Okay? So, but the clock skew, you have a mean value of your clock delay, and then you have a clock skew is basically this delta that I have between the fastest and the slowest elements. So, let's look at skew. There's two ways of playing around with skew. Suppose I have now a data path. Okay? Flip-flop, logic, flip-flop, logic, flip-flop. Okay? In the ideal case, all those registers would see exactly the same clock edge. But now suppose that the data obviously in this design goes from this here to here, right? That's the direction of my data flow. Now, I can route the clock in two different directions. Routing is basically the wire where the clock propagates. So if I basically insert the clock here and then have a wire running in the same direction of the data, we see that here TCLK1 is when the clock arrives at this register. Then there's some delay. We see that TCLK2 will arrive a little bit later because of the RC delay of that wire. Okay? And going in the other direction. So you see that in this case the clock travels in the same direction as the data. Okay? That's what we call positive skew. This will have a skew, TCLK1 and TCLK. TCLK1, if you have TCLK1 here, that's the edge of that clock. TCLK2 will be like this. And the difference between those two we're going to call delta. And we call delta positive if the clock edge at the destination register arrives later than at the transmitting register. Okay? So that's positive skew. Negative skew is the opposite. I actually could do the opposite thing. Okay? I can route the data, the data still goes in this direction here, but now I take the clock and feed it from the other direction. I'm just wiring it the other direction. So the clock arrives first here, then here, then here. So in that case, we will have TCLK1 will be like this, and TCLK2 will be arriving earlier. Right? This is again delta, but in this case we're going to call delta negative. Okay? The clock arrives earlier at the destination register than at the source register. Okay? Now, let's think what this does to us. Suppose I look at propagation delay, a clock period. And let's take positive skew. Okay? Just think about it for a second. I have this latch here, clock comes in, I have my data, and I have arrives here, but the clock TCLK2 will arrive a little bit later than at the source. What does that do to my clock period? The worst case, remember the clock period has to be longer than the longest path in the logic, right? Will this allow me to clock my circuit faster or slower? I have some skew added. So remember, you have a certain, suppose you have no skew, you get a certain period t, right? We have the equation for that. Now I add some skew to it, positive skew. What do I think? And I can basically clock the circuit faster or slower? Or the same? Will it help me or will it hurt me? That's really the question that we have to look at. Remember what yes, Ben?
Faster.
It's faster, yes. And could you explain why?
There's an extra delay between the second and the first, so you have that extra delta for it to finish computing the logic.
That is correct. Actually, what you get is, so because the clock edge at the receiving edge arrives later, it sounds like, it looks like you have more time to do your computation. So your clock edge comes in, your data starts traversing, and now the clock at the other arrives a little bit later. It means I have more time to compute, which means that I basically can go faster. I basically can have so that's a very positive type of thing. Now let's look at the other case, negative skew. It's going to be the opposite, right? There, clock edge starts, and now I'm basically going to start, my data start propagating, but I have to be ready earlier because the clock at the receiving edge is going to be there too early. And I have to be ready for that. So positive clock skew is good from a performance perspective. Negative clock skew is bad from a performance perspective. So that's good, right? So here's rule number one. I'm a clever designer, so okay, cool. I'm going to make sure that I always have positive clock skew. I route my clock very carefully in such a way that it always travels in the same direction as my data. Now, that's the good news. However, there's some bad news too. Let's look at the other constraint. The other constraint is my minimum hold time. Think now what's going to happen with my positive skew case. I have a clock. I add, basically I apply my clock edge, and now again at the receiving edge, I'm basically going to delay the clock a little bit. Remember the hold time constraint? It says, you have to make sure that the minimum path is shorter than the hold time constraint. But now that flip-flop moves back, I use basically the clock edge backwards. It means that it's going to be harder for me to meet that hold time constraint. That minimum clock path, but minimum delay is the same. But now I'm moving my edge, so it's going to be a lot easier for me to violate that hold time constraint. So yes, you can play with fire. I start and push. I basically add skew, and I move on, move on. I get higher performance. But suddenly, bingo, you violate the hold time constraint, and that thing doesn't work anymore. Now let's look at the other side. If I have a negative skew, could I ever have a hold time constraint happening in that particular case? So again, now you have your clock coming in. Your clock starts, and the data starts racing really rapidly through the logic. That's the minimum delay path. And we have to make sure that it doesn't get to the flip-flop before that flip-flop basically has had its hold time constraint. But now I move this thing forward. I already add a negative time to it. So this data starts, and I basically move this, and actually violating the hold time is almost going to be impossible because you already have clocked it before the data starts even racing on this side. So negative skew is very good if you want to avoid hold time constraints. So that's kind of an interesting type of observation. Skew helps me to play around with clock edges. So positive skew, we've seen this. It moves the clock backwards. We've seen that. Negative skew moves the clock forward. We discussed that. So timing constraints. So if you look basically as a minimum cycle time now, what clock skew does is the following thing. Remember, minimum cycle time t has to be larger than the largest delay with C2Q plus T setup plus T logic, right? Now, positive skew basically kind of extends the period that I can work on. I have more time to compute. So T plus delta has to be larger than this number. Now, if I move delta over here, it looks like I'm subtracting this clock skew from that delay, and which means that my clock period can be smaller, which means that I can clock it faster. Okay? If you have negative skew, it's the opposite. Negative skew, if you put here as a positive term, it means that my clock period has to be longer. Okay? So that's case one. Let's now look at the hold time constraint. So the hold time constraint says that the minimum speed or the minimum delay to your logic, C to Q, plus the minimum delay to your logic has to be larger than T hold. But with clock skew, we basically move this thing backwards. We increase the chance that we're going to go in trouble. So we have to add delta to T hold. It's like we're extending the hold time constraint. So it shows that when basically delta is positive, when you have positive skew, it's going to get harder to meet that hold time constraint. While if it's negative, we make it easier. So if T hold is 0, negative basically means that we're always going to meet that constraint. So we have no problem whatsoever. Okay? So these are two very important equations to remember, because these are at the core of all the timing verification work we're going to do on a chip. You have to make sure that this relationship are always valid. If not, we're going to be in deep, deep, deep trouble. Your chip might not work at all. Actually, it turns out that if I use edge trigger flip-flops and I have a hold time constraint, you're toast. You can just throw the chip away. There's nothing you can do. Say, well, maybe I'm going to slow down the clock a little bit. No, because this has nothing with the clock period to do. The clock period doesn't appear in here. This is just a pure property of the delay of the logic versus your hold time constraints of your registers. So you just throw it away. There's nothing you can do. So that's bad. And that's why people check on hold time constraints very carefully. Okay? All right. So now we have studied deltas, the clock skew. What would jitter do to you? So the thing about skew, it's a directional property, right? It's something that is deterministic, but has some variance to it as well. So you have to basically take care of the worst case, right? The worst case type of deltas that you can get. Now think a little bit, what would jitter do to you? Would jitter, and remember jitter is this thing that on a local clock, from clock cycle to clock cycle, thing go brrrr, goes back and forth. You don't know exactly where it's going to end because there's some random component added to it. Because there's this noise on the supply rails, coupling from other guys, all this kind of stuff. So think about jitter. Could jitter help you, or would it hurt you? From both clock period performance perspective and hold time perspective. What do you think? Let's think first of all clock period. Can I clock, if I have jitter, would it would it allow me to go faster or slower? Any thought? Yes.
I would think since only the voltage is changing, it's going to change the slope of the clock, but the 50% point should stay at the same time, right?
No. The 50% point changes. Right? So noise basically changes the delays of your buffer. So your clock goes brrr. And basically, if you look at it on an oscilloscope, you will see some kind of gray fuzzy area, right? Where you expect the clock edge, your clock will go brrr, left and right, left and right. It will be fuzzy. From one clock cycle to the next, it might be here, 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 at the same edge. So it's a random variable that you add to that clock edge. That's really what jitter is all about. So again, would it help you? Would it hurt you? Anybody thinks it's helping you?
Well, I think you can't make your clock faster than that jitter displacement, right?
That's right. Because jitter is a random component. You don't know it's going to be positive. You don't know it's going to be negative. From cycle to cycle, it can vary. And it can go this way, it can go this way. So it can be positive, negative at the same time. So you cannot count on it. So you always have to go for the worst case of the jitter. Jitter always is going to work against you. It's a bad thing. Trying to keep jitter down is a really good idea because it's a random variable. It might be that because of jitter, my sending clock might be late and my receiving flip-flop might be early, right? Or it might be the opposite. You don't know. From clock cycle to clock cycle, this can vary. So I always have to budget for the worst case jitter that is appearing. So if you look at it from an equation perspective, you see that jitter, if you look at the logical, here's the logic delay. You have TCLK, we add delta, we have done that before. But we always have to subtract the jitter at both sending side and receiving side. It's always working against us because we can be late on one side and early on the other side. So we have to work for the worst case that can happen. So we really have, and if these are the same, let's assume now that the jitter at different clock edges is the same, we really have to subtract 2 times T jitter. Or from an overall clock perspective, we bring this to the other side, we see that it basically increases the clock period, makes us go fast, slower. The same thing is true from the hold time perspective. There it can work in the negative direction in both ways. So again, we have to add it 2 times to it. Oh no, this is not the jitter yet, this is the same thing. So you can see that TCLK, clock period, is maximum delay minus clock skew plus 2 times the T jitter. So positive clock skew help, negative clock skew is bad, jitter is always bad. Okay? Shortest path, we know that. We can change. So you can see that jitter basically, again, hurts us, and we have to make sure that we add 2 times T jitter to this here. So the minimum delay of my logic has to be larger than T hold plus 2 times T jitter plus delta. Okay? So jitter is something that you would like to stay in. And that's why a lot of people spend a lot of time on this. A lot of the jitter actually comes from this phase lock loop, this magical thing that sits there. That's a major source of jitter. So you'll see a lot of papers in magazines where people talk about how can I create a phase lock loop and an oscillator, voltage controlled oscillator that minimizes the jitter. Very important element. Okay? So these are important things to remember. We're going to come back on later on how to do clock distribution schemes that help us to manage skew and jitter. That's a little bit later because I have to talk about wires before. But remember, there's ways of dealing with skew. If I wanted to have an ideal design, what I would like to do is design a clock network where all the clock edges appear at the same time. That's kind of safe, right? Then I don't have to worry about anything. However, because of skew reasons, sometimes if I'm basically daring, I can try to play around with positive clock skew. Some people do that. You have, let's say, a data pod like this one here. I have a data pod in a processor. If I manage to get the clock to drive in the same direction as the data, I can clock it a little bit faster. You know, good high-performance designers do this type of things. But then, as I said, then you better make sure that you don't violate any hold constraints. Because if you do so, boy, I said you're in deep doo-doo. Okay. A couple of words before we finish with timing. A couple of words about pipelining. Who's ever heard about pipelining? Where do we teach that? Probably this C1C does that. Yeah, we talk about pipelining, right? Pipelining is a form of concurrency. All right, suppose I have to perform this operation. I have 2 data streams coming in, A and B. You go to a register that's getting clocked. It's like our project in some sense. You have an adder, absolute operator, lock operator, and so on and so forth. So in a non-pipelined operation, what happens is that the critical path through this logic is going to be the sum of all the delays of all the individual elements. Right? So my delay is going to be C2Q of the registers, delay of the adder, delay of the absolute value plus the log, and then basically the setup time of the register. Okay? One way of speeding this up is to say, well, gee, I'm going to break up this critical path into pieces. I'm going to put registers in between. Okay? In this case, I had 2 registers. What does this do? Well, the result now is that the critical length of every one of the elements gets smaller. Right? It's now the C2Q of a register plus the delay of 1 block plus the setup time of 1 register. So this can be clocked faster. And the advantage of this also is that I now perform the addition, the absolute value, and the log operation in parallel. It's concurrency. Because when I start, initially, it's clock phase 1, I do an addition. That goes to the next stage. So I do A1 plus B1. In the next clock cycle, this moves to the next stage, goes here. I do the log value on it. Next clock cycle, I'm going to do the log. But while I'm doing so, already in clock cycle 2, I can do the next addition. And clock cycle 3, another addition. So you have additions going on simultaneously with absolute values and log operations. So you create a lot more concurrency. Your hardware is going to be a lot more busy. Because like in this case, you start with the absolute addition. The data goes like a wave forward. Once the addition is done, this adder hardware is empty. It's idle. It doesn't do anything. While pipelining, you keep everything busy all the time. Okay? So that's a very effective way of doing things. But you have to also be aware that it's now going to take a couple of clock cycles before the input appears at the output. And it's not something I always can do. For instance, if I have logic which has feedback into it, where I take some results that come out and I feed them back into the input, just adding registers in here might mess up your whole computation. You might add the wrong thing to the wrong thing. So you have to be careful when you do pipeline. But pipeline is a very effective approach to play around with. Now, pipelining is a place where we actually can use latch-based clocking quite effectively. Because now, suppose, let's say, that I would do a pipelined logic structure, and I try to do edge-triggered flip-flops. Right? So I have edge-triggered flip-flops, and I have logic. Edge-triggered flip-flop, I try to do logic. And I say, okay, I'm going to make it fast. I'm going to use domino. Okay? Domino logic in here. What you will see is that I'm going to have a clock which is composed of two components, right? You have a clock that first goes negative, and this phase we do the precharging, and then in the second half of the period we do the evaluation, we do the computation, and then finally we can latch it into the next register. Which means that the clock period I'm going to use in this case is going to be what? It's going to be the fact that I first have to do precharged plus followed by basically evaluation. The clock period is going to be determined by the sum of the two. So dynamic logic doesn't help me very much because I have to absorb both precharge and evaluation period. Now if I use latch-based approaches, you can do a little bit cleverer. Suppose I have a latch here, and I call this a CLK latch. Then I have logic, and I have a CLK prime latch. Then again a CLK latch. Now what you can see is that by varying the different clock phases on the consecutive blocks, as you have to do with latch-based design anyhow, I can kind of interchange precharge and evaluation. So for instance, when the clock here, let's say this is a clock bar, when clock is high, okay, this register is going to be in evaluate mode. The data comes to the output here. In this case, that block should be also in evaluate mode. This register is off. In that case, I basically can put block G in precharge. So you have evaluate, precharge, evaluate. Next clock cycle comes in, we turn it all around. If you look at it effectively, we're going to save substantially amount of time. I actually can reduce the clock period substantially now because I basically interchange precharge and basically the evaluate type of mode. So that's why if you basically want to do domino logic in a pipeline type structure, you're never ever going to use edge-triggered flip-flops. It's a really bad idea. So here I am, I'm doing a lot of work on making fast logic, and then I start putting edge-triggered flip-flops in there. I'm losing most of my advantages. While with latches, I get around that. I can basically kind of interchange, overlay, precharge, and evaluate modes. It's a lot faster. So that's just something I wanted to mention before we go to the next thing. Okay? I'm not going to tell you a lot more about latch-based clocking. It's complex. It's not easy because checking on hold times and checking on setup times, hold times, and setup time violations and all these kind of things is a lot harder in these circumstances. And you can play very special tricks, but again, I'm not going to go into detail in that. So this is something you have to remember. If you think about clocking and timing, latch-based design versus flip-flops. In a flip-flop based design, Data launches on the rising clock edge. If the data arrives late, the system fails. And that's obviously a problem. If it arrives early, we're wasting time. Right, so in a register-based thing, you want to make sure that you're kind of sitting on the ideal case. Latches are kind of weird. Latches don't have really that strong, that very sharp edge type thing. Because when the thing is transparent, it it's okay. The data doesn't really matter if it arrives there a little bit earlier or later. We're fine with it as long as they're there before the total edge. So you actually can start doing the next computation while the previous one is still going on. This is what we call time borrowing. Again, I won't tell you more about that. That's really 241 material. But you have to be aware at least a little bit about the different trade-offs and why it is that people don't always use registered edge-triggered flip-flops. They're the easiest ones to use. They're easy to analyze. But actually, if you want to go really fast, latches have some advantages. Bottom line. Okay. That's about timing. We'll come back to it. But I said if I really want to understand timing on a chip level, I have to understand a little bit what wires do. Because you think about it, the clock is nothing else than wires and buffers. That's your clock signal. You have a source, you distribute it everywhere around, and you buffer it out. You want to make sure you have some nice clock edges. It wouldn't pay very well to have a clock that looks like something that goes very slowly upwards and eventually makes it and then goes down again. That's not very nice. So a good clock is sharp, very well defined, arrives always at the same time, things like that. So how to do that is going to be a challenge. But as I said, we first have to understand wires. Okay, so wires. Doesn't sound very attractive, right? Thinking about wires, it's kind of boring. Right? Good designers like to basically play around with transistors, weird logic styles, all those kind of things. Who wants to worry about wires? It's the most mundane topic in the world, but it's very important. As I just mentioned at the beginning of the lecture, if you think about high-performance design today, most of the capacitance you're going to drive in your logic is not going to come from the gate capacitance, but it's coming from the wires, the metal wires that are out there. So understanding what those wires do and how to get around some of those problems is very important. So, the wire. So, in schematic, life is beautiful. Right? We do a schematic diagram and we draw a lot of transistors and all this kind of thing. And then you have these ideal little thingies that this wiggles basically just a straight line. That's what a wire is all about. It looks like a dimensionless thing. However, on a chip, this is not the case, right? If I look at the same wiring structure here that I just showed you here, in reality, wires have thickness, they have a height, they have a separation. So they're really three-dimensional entities. And if you look at a real chip today with 9 metal layers, you can imagine this kind of like it's almost like the overpass when you go from Oakland to, let's say they're on 980, layers and layers on top of each other, kind of crisscrossing over each other, connectors between them, and so on and so forth. Three-dimensional structure, really, where things are kind of overcrossing, connecting to each other, all this kind of stuff. Most of those wires are so high up in space that they barely see the substrate that's at the bottom of where your transistors are. Right? You can imagine that, right? If I'm basically at level 9, the substrate where the transistor is very far away. So if you think about from a capacitive perspective, the capacitance there is going to be quite small. While I'm going to see all those wires next to me, that's going to be a much larger capacitance. So worrying about the capacitor wires neighboring you is going to be more important than basically worrying about capacitance to ground. Okay? So that's what we worry about. This ideal wire, if you really look at it, this three-dimensional structure, and I want to model this effectively using all the effects that are included. That's really what the wire looks like. It has capacitance to ground. It has capacitance to neighboring wires, as I just mentioned. 2 wires next to each other, certain thickness, dielectric in between them, bingo, capacitance. They have resistance. They're not ideal material. We used to do aluminum. Most of the time right now, it's all copper, which is good. Copper is better than aluminum, but you still have resistance. They have inductance. If I have two wires running next to each other, I make little inductive coupling. If you have current flowing into things, as we create loops, you have little magnets. Well, not magnets. You basically have coils that basically interact with each other using magnetic fields. So inductive effects. Now, fortunately, most of the time, if you don't really go gigahertz of frequencies, I'm not going to worry too much about the inductors. It's only when you have very sharp edges and when you clock things at rates at multiple gigahertz, then you have to start worrying about the inductive effects. Most of the time, we deal with only resistors and capacitors. In the most simple case, we only have to deal with capacitance. Right? That was what we did 10 years ago. So wires are capacitors. And what they do is present a capacitive load to my drivers, to my gates. And it adds to the CL. Typically CL, the load capacitance of a gate consists of the fan out, the gate capacitance of all the gates connected to it, plus the metal capacitance or the capacitance of the wire. Today, when the wires get a bit longer, you have to start worrying about resistance as well. Okay? So, what can wires do? Well, they're bad for everything. Right? There's no good thing. If I would have ideal wires, we can make something superconducting, no resistance. If I have an ideal dielectric with very low dielectric component, for instance, air. If I can make my wires in air, capacitance is going to be very low. That's what else would be very nice. But it's kind of squishy when I have all my wires kind of sitting there in the air. Not easy to do. But they add to the cost. They impact reliability, as we'll show. They impact performance, and they impact power consumption. Obviously, more capacitance, more power consumption. And as I mentioned, we have capacitance, resistance, and inductance. So what we're going to do now is go in sequence to each of those. Talk a little bit about capacitance, talk a little bit about resistance, and I think it's worthwhile to know a little bit about inductance as well. Because you might not worry that when you do a 100 megahertz design, but when you do a couple of gigahertz stuff, you better be worrying about inductance. And it also helps you explain some things that you might observe in an oscilloscope. You look at a signal on an oscilloscope, sometimes you weird thing. Most often, that's because of inductive effects. Okay. So, here's kind of an interesting slide. I take a chip. And I take all the wires on the chip that I have. So I take here, this is a set of Pentiums. Okay, Pentium MMX, Pro, Pentium 2, Pentium 3. These are 0.5, 0.18, and 0.13 micrometer channel. So these are microprocessors of, about a couple of years ago, 5 years ago approximately, at least the last one. Take all the wires on the chip, the short ones, the long ones, and I plot a histogram. Okay, so here it is. This is the net length, the length of the wire. This is the number of nets of every length. So that's a typical histogram for those different things. And what you get is very often a distribution that looks like this. Okay? They always look pretty much the same. What it says is that you have a lot of very short wires, which is to be expected, right? I take a ALU, I take a multiplier. Within there, you will see a lot of wires that go to a couple of gate fan out. That's basically implementing your logic. Okay? And then on the other side, you also have a selection of wires that are very long. Buses, interconnection between blocks. Let's say if I have to go from my ALU to my memory, if I have to go from my register, from my instruction register to the data path, you have all these control signals that basically go out there. They might go over long distance. So now, interesting to think about what's going to happen when you scale technology. What's going to happen with those wires? Are they going to get longer? Are they going to get shorter? One thing you might say, well, gee, scaling technology means that all my transistors get smaller, my logic gets denser, everything gets close together, so the wires should get shorter, right? And indeed they do. Those wires here scale like the technology. Smaller, if I basically scale my technology with a factor of 0.7, typical, the wire length of those wires is also going to go down with a factor of 0.7, which is nice. Right? They basically remain the same. However, the long wires don't do that. if I basically keep my chip size at a centimeter, let's say, I have a processor, I always going to keep it at a centimeter, while the short wires get shorter, the long wires actually going to remain approximately the same length. Or if I make my die bigger, they're actually going to scale like the size of the die. So two very opposite scaling effects. Short wires get shorter, long wires get the same length, or basically grow in length. They scale as the size of the die. So we'll see very different behavior between those two. And those worry me, but those worry me even more, because they're going to have a very nefast impact on the speed of my design. So that's important to know, because there's a lot of the scaling rules we're going to play around with are going to be driven by this. We have to understand the scaling behavior of the length of the wire. And as I said, it's not uniform. Like transistors always scale in the same way. In scale technology, all the transistors scale down, right? But not wires. So let's first look at capacitance. Capacitance of a wire. So this is a good old wire. It's long ago that I've seen a wire like this. This is your wire. It has a piece of metal, right, with a certain height, length, and width. Okay? Sitting at a certain level. And in between them is dielectric. Used to be silicon oxide, often also silicon nitride. That was the typical material we were using as a dielectric between the different metal layers. Okay? So let's assume that the current flows this way in the direction of the length. Now the capacitance of a wire like this is mostly followed by, suppose this is sitting on a ground layer. So you have a ground layer, substrate, dielectric wire. This is 117 material. Kind of, well, it's probably, you've seen it earlier on as well, but 117 is a class where they do a lot of this kind of analysis. So you have an electric, so what you see in this case, if the width of the wire is fairly large, most of the capacitance is going to be formed by the electrostatic field between the wire and the ground. So you have an electrostatic field, you have electrical field lines going from one to the other one. And you know that the value of the capacitance in this case is going to be equal to epsilon over T times the overall area of the capacitor. This is what they call a parallel plate capacitive model. Right? You take the whole area of the wire, W times L, and the overall capacitance is multiplied by the capacitance per unit area is epsilon over T, where T is the thickness of the dielectric. So thinner dielectric, larger capacitance. Okay? So scaling down technology is not going to help in that perspective. If we put our wires closer together, we have some problem here. So let's now think what's going to happen if we scale this. We go from technology A to technology B. Okay? And we assume we do ideal scaling. Just like we do transistors, every dimension scales in the same way. Okay? Well, in that case, let me make one exception. As I showed you, the length of the wire can scale in different ways. If you have a local wire, it's going to scale like the technology. If it's a global wire, it's going to scale like the size of the die. Right? So we get the following thing. The scaling factor of the capacitance of a wire is S. Assume that we don't change the dielectric, same dielectric material. So we get S over S. So this thickness of the wire and the width of the wire scale in the same fashion. Okay? Or sorry, the thickness of the dielectric and the width of the wire change the same way. They fall out. Really what it scales is 1 over SL. So if S is positive, it means it scales like the technology. We see that the capacitance actually is going to go down, which you would expect linearly. If the capacitance basically, we get this wire, it gets shorter with scaling of technology, we see a linear reduction in capacitance, which is nice, because remember the propagation delay and things like that also scales linearly with scaling of technology. So it's, from an overall scaling perspective, this is beautiful. However, for long wires, it's just the opposite. If the chip length, chip size remains the same, actually your capacitance of your wire is going to remain the same as well. If your chip gets bigger, with scaling and do larger die size, actually your capacitance actually is going to go up. So that's already a worrisome factor, is that the capacitance of the wire scales like the length of the wire. Now, this is the beautiful perspective. This is the world in the ideal space. However, oh, by the way, before I go though, so let's also think a little bit about the dielectric material. I said this is where we're at. Remember the relative permittivity of a material is the permittivity of a dielectric is the permittivity of that dielectric divided by the permittivity of air. Right? So air, free space, has a permittivity of 1, or relative permittivity of 1. Silicon dioxide has 3.9. If you go on a board level design, that's epoxy. Most of the time as the material you're using there, it's even worse, it's factor 5. So it gets you more capacitance. There's some polyamides, which are organic materials. Organic materials actually can allow you to go a little bit lower than silicon dioxide. It's a this is called a low K material. Sometimes people use K instead of epsilon. I don't know why, but they use K. So if you hear somebody saying low K materials, that means low epsilon, low relative permittivity. Okay? So polyamides is what the industry is using today. Say, before that, silicon dioxide was the premier thing, but then they figured out they had too much capacitance between the wires. So they said, let's use something different. So the industry switched to polyamides. Really, if I want to keep my capacitance small, and obviously keep capacitance small is a good goal, right? It's faster, less power, all this kind of thing. So actually, people are playing around with aerogels right now. You obviously cannot use air. It's not easy. Some companies have tried. You put your metal wires down, and you put another one over it, and you have a dielectric or something in between, and then you etch everything away. So you basically first build your structures with all those wires and all the thing, and you have some what they call material that's disposable in between, and then you put in some etching material, you etch everything in between away, and now the wires kind of float in the air with some anchor point, obviously, which are your vias. But you can imagine that's kind of a little bit brittle. If there's some pressure on your chip, you might have some short circuits or your wires might break. So some companies have tried this, but it's not very effective. So what the newer things that people try to do is this, aerogels. It's like an aerogel is like a polyamide. It's like a polymer style material, organic material, like a little rubbery type thing, and you put little air bubbles in there. So by air bubbles in there, you reduce the permittivity of the material, and now your interconnect becomes kind of squishy. Right? You kind of push it together, but it doesn't really going to create any short circuits or anything like that. So you might see in the future chips that when you push on it, they kind of go back a little rubbery on the top in some sense. So that's those aerogel type thing. So see, people try to do a lot of things to make capacitance smaller, because as I said, capacitance is becoming a larger and larger factor. Now, now you might wonder, it said, well, if local wires scale like the technology, so why bother about all those things? Why not just stick to silicon dioxide? Because it's going to scale anyway. It scales like the propagation delay. That's not the case, however, because there's some other things that happened. Turns out that wires used to be like this. Okay, this is a typical wire on a chip. It's a nice rectangular thingy. What we have done with scaling of technology is that we have reduced the width, but we decided not to scale the height of the wire. Okay, so instead of keeping like this, what we have done is make it like this and like this. So the height of the wire has remained the same for a good reason, which I'm going to show you after this when we talk about resistivity. If you just scale all dimensions of the wire in the same way, the width, the height, you see that the cross-section of the wire is going to go down. You can imagine that the cross-section, smaller cross-section, typically going to mean higher resistivity. And resistivity is bad, because now you start to get RC delay. So we couldn't do that. So we said, well, gee, instead of scaling down the width, we have to scale down the width, obviously, because otherwise you cannot connect to your transistors anymore. The transistor is getting smaller, and need thinner wires. So we kept the height of the wires the same while scaling down the width. So what the result of this is that wires now look like this. They're reverted. Instead of flat rectangles, they're basically standing on the side almost. And I'll show you some pictures that cross sections of metal stacks that show that's exactly what's happening. Now think about it. If you think now about capacitance to ground, here's my ground, and I have a guy like this. Yes, you have electrical field lines going like this, but there's also going to be electrical field lines coming off the sides. The idea that this is a perfect parallel plate capacitance doesn't hold anymore. There's a lot of field lines spreading around. So all three corners of the wire now start adding to this electrical field. This is what we call fringing capacitance. It's a fringing field. It fringes around and goes that way and increases the capacitance. Okay? So the capacitance of a wire now is the parallel plate capacitance, CPP, plus the fringe capacitance on top, which is going to be proportional to the basically the side wall of this capacitor here and the thickness of the wire. Now, trying to solve the parallel plate capacitance is easy. It's epsilon over T times the area. That's easy. This one is a lot more tricky. So this is your parallel plate capacitance. Trying to find an exact expression for the fringing cap, you know, that's what you're going to learn in 117. They're going to put some charge on the thing and say, compute the electrostatic field and have a lot of fun, and you get these long, long equations that eventually lead to something. But people have always tried to figure out how to simplify them a little bit. Bottom line for you to remember is that there's going to be a fringing capacitance that we have to express. And typically from a process guy, if I go to a fab and I say, okay, what's the capacitance for layer 1, layer 2, layer 3? It's going to give you parallel plate capacitance numbers. And they're also going to give you a fringing capacitance per unit length of the wire. So if this wire is a certain length, you're going to be per side of your wire, you're going to get so much fringing capacitance. So if I now want to compute the total capacitance of a wire, say I'll take CPP, that's the parallel plate capacitance, which is capacitance per unit area. I multiply this with the width of the wire times the length of the wire. That's the area of the wire. And then I take the C fringe and I multiply by 2 times the length of the wire. Now why 2? Because there's two sides of the wire. Right? There's one on the left side, on the right side. So that's the wiring capacitance. The interesting part is this used to be the dominant factor by far. The smaller we scale my technology down, this factor becomes more and more important. And today, more and more we see that fringing capacitance is just as important, if not more important, than basically parallel plate capacitance. This is already an old slide from '89, but it's still pretty much valid. It basically says that if you look at W over H, so if you have a wire which is a lot wider than basically the height of the wire. So we have, let's say, T over H is the same. So if the wire is a lot wider than basically the height of the wire, okay, in that case you see that all your capacitance is going to be coming from this parallel plate capacitance. This is the total capacitance. This is the parallel plate capacitance. You can see W for a rectangular wire, flat wire, all the capacitance is parallel plate. Now, if you make the width of the wire smaller and smaller and smaller, we see that fringing capacitance, which is the other component, starts to get larger and larger, and ultimately dominates the capacitance. If you look at WH over 1, we see that the capacitance is equally divided between fringing capacitance and parallel plate capacitance. Okay? So don't ignore this. It's an important factor. It's getting more and more important. It's pretty amazing. If I look at transistors at 32 nanometers, it's kind of scary. You see your transistor sitting there. This is your channel. Here's your drain source region. You have your gate stack. And then you have the wire connecting to the drain and source. And you can see these towering things sitting on the side. This is this metal thing connecting to the drain and the source, or polysilicon, or whatever it is. They're like towers. It's not the picture we used to see of a transistor. It's a very different, convoluted world these days. Okay. That's the other part that you have to remember is, as I said, okay, fringing capacitance is important, but there's other factors. If I have only one metal layer, or one polysilicon layer, let's say for interconnect, obviously most of your capacity is going to be capacitance to ground. And I might have, if I put my wires very close together, this height is now getting important as well. So if I put two of those very thin, skinny things next to each other, you can imagine that the capacitance from here to here is going to be important as well. That's the wire-to-wire capacitance. Wires that are basically routed next to each other are going to have a fairly large component of wire-to-wire capacitance. Well, if you put multiple layers on top of each other, this is level 2, you can see you're going to have both parallel plate capacitance and fringing capacitance between wires. So now you get this very convoluted picture of wires on top of wires on top of wires, with all of them having capacitance to each other. Now this is not capacitance to ground anymore. And remember, 7 weeks ago, when we talked about capacitance, we said, you know, most of the capacitance to ground, we like capacitance to ground, right? The input goes out, you know exactly what the delay factor is. Those capacitances that are floating are a lot more painful. Right? It can, if one side goes up, the other side might go down, they might go up together, they might do weird things. Floating capacitor, in terms of impact on delay, is a lot harder to analyze than as something which is purely grounded. You can have Miller effect, for instance, or similar type of thing. So interwire capacitor is very important. And let me show you why it can be important. But before that, again, we see that if you scale down technologies, more metal layers, we see that interwire capacitance starts to become dominant. And that's the case today. I think more and more of the capacitance on a chip is not my wire sitting over a ground plane. It's really all those wires interacting with each other. Now let's look at some scenarios of interwire capacitance. And it's kind of interesting to see. Suppose I have 3 wires. Okay, 3 wires, and I route them next to each other on the same layer. Okay, layer 7 or something like that. So they're going to have interwire capacitance, right? This is C1. They're also going to have some capacitance to ground, but let's assume that the capacitance to ground is quite small compared to the interwire capacitance. No, I want to raise this thing here. I have a capacitance C here, a capacitance C here. And obviously you have a capacitance to ground. Now, what is the total capacitance that, so let's call this wire X, Y, Z. What's the total capacitance? Let's call this CL, and then we have CC. And assume that they're the same. What is the total capacitance that node X sees on a transition from low to high? Any suggestion? So I have this situation here. I have a capacitance to ground, and I have capacitance CC to 2 neighboring wires. Can anybody suggest me what the total capacitance is that I should take into account for wire X? Okay, so the voltage. Okay, suppose I put both of them at VDD. What would I see in that case? Make it ground. Same thing. So what's the total capacitance I see? Yes? Yeah, so it's CL plus 2CC, right? And they're all capacitors to ground, right? Or to VDD, doesn't matter. It's DC. So that's a typical situation. But now, these are wires too. They carry signal. Suppose now I do something different. I have both of them, all of them doing exactly the same thing. They all go high at the same time. It's a bus. And they all basically go from 0 to 1 at the same time. What's the capacitance in that case? Sorry? That's right. CL. Because the CC is basically see the same voltage at both ends. They go both up. There's no charge going on there. So it means that the capacitance here is going to be smaller. Now let's do another thing. They go both the opposite way. What do we see in that case? That's right. So what we see now is that when we have capacitance that mostly consists of interwire. If most of the capacitance is interwire capacitance, we see that the real capacitance that the node sees is a very strong function of what the neighboring signals do. This is a huge variation, right? From CC, or basically purely CL, to CL plus 4CC. That's a huge variability. So it means now that the load capacitance of this wire is going to be a function of the signaling. And that makes your life a lot more complicated when you want to do analysis. That's why interwire capacitance is really painful. It's like Miller capacitance in the past. It's floating, and you really have to know what's happening on the other side of the node to figure out what the real capacitance is. So this is kind of sketched in this this set of slides here. I don't think I have gone through all of those. You should be given the answers to each of those. So the bottom line is that the capacitor volt has changed substantially. We have now a whole much more complex perspective on what's going on. And typically now when I go to a fab, I'm going to get obviously my transistor models. That's important. I'm going to get my SPICE models or spectrum models, the transistor behavior. But I'm also going to get tables like this, which give me an idea about the capacitance between different layers. Okay? Capacitance between aluminum 1 or copper 1 and ground, aluminum 2 to ground, aluminum 3 to ground, or aluminum 1 to aluminum 2, aluminum 3 to aluminum 3, and so on and so forth. So we have this basic set of capacitance, and based on that we can compute all the capacitors in the structure. Now doing this is very hard by hand. So fortunately, CAD guys have non-stance stood still. Typically what's going to happen is I can take a layout with all the layers and all the metal wires and so on and so forth. You feed it in there and they're going to try to compute for you all the interwire capacitances and take that into account. Because it can be complex, right? If you have a wire that goes like this and there's another wire that crosses over a bit and goes like that, what's the capacitance between those two wires? Right? There's fringing fields, there's direct paraplate capacitance, all those kind of things. Fortunately, this is all solvable. You have very nice 3D field solvers. They solve all those things for you. So the good news is you don't have to worry about the tools are there, but you have to at least be aware of the fact that interwire capacitance is very important. Okay, so that's the conclusion of this whole thing. So that's where we really are, capacitance. And what I'm going to do next lecture is go from pure capacitance, start talking a little bit about resistance. That's the next step we're going to have to look at. And there I already, I think, can give you a short intro on what to expect. As I already showed you before, the problem with wires is, let's say I have a wire like this, and I scale it to something like this, we see that the resistivity of the wire, obviously a wire has a resistivity. Resistivity is a property of the material, right? So if I now scale a wire and I scale all the dimensions, what's really important for the overall resistivity per unit length is going to be this cross section, right? A fixed current, if I have a fixed current, then I basically want to figure out how much voltage I'm going to get. If I make the cross section smaller, you will see that the voltage is going to increase. Or in other words, that the resistivity per unit length is going to go up, which is not good, because I like to see a wire like this. A wire which is pure capacitance means it's instantaneous. Right? If I have a wire from here to here and it's purely capacitive, if I apply H here, it's going to appear right away at the other end as well. There's no delay in a wire. However, if I start adding resistivity to this thing, you start adding delay. And now your delay of your whole circuitry is going to be delay of your gate switching, as well as the delay of charging this capacitor to a resistor. So we see that this is becoming a more and more important factor, and that's why we have gone to copper. Copper is a better material than aluminum. Aluminum was kind of lousy. Polysilicon is even worse. So polysilicon, aluminum, copper. We could go to silver. Silver is even better. It's actually the best material we could use. But the problem with silver is that copper doesn't like silicon. They don't like each other very much. Copper tends to diffuse. When you put copper right on silicon, it diffuses into the silicon, and it destroys the semiconductor properties of the silicon. So your transistor wouldn't work very well anymore. Silver is worse. Silver and copper hate each other. Silver and silicon hate each other altogether. So nobody's even trying. Copper, they figured out how to make them kind of make friends. They're never going to be good friends, but at least they can coexist with each other. What they do with copper is say, okay, I make a copper wire. I'm going to put a little thing around it so that it doesn't get in direct contact with the silicon so that they don't fight each other. And this is called the Damascene process that IBM discovered about 10 years ago. So they figured out a way to go copper. I don't think we'll ever go to silver. So copper is what we get. We're not going to get any better than that. So there's little gain to be expected. So what we're going to do next lecture is talk a little bit about resistivity. We'll talk a little bit about inductivity. And then we're going to talk a little bit about how to deal with those effects. By what circuit techniques can I use to deal with some of the effects of wires. Okay? See you on Friday. Yes.